Okay, so when we're analyzing graphs, again, we're reading what we have, what do we have in front of us, and what are we looking for, and then kind of translating that into what we know. Okay, so a particle moves along the x-axis, so that velocity goes from 0 to 18. Starts at 0, goes to 18. Or sorry, time goes from 0 to 18. Again, the graph they give us is the derivative graph. This is the derivative graph. This is velocity. Okay, so using that, again, it's not green. I know it's not green on yours, but there's two little dots on there if you can see them. These are inflection points. Inflection points for the original position. Because remember, position is the original. Velocity is the first derivative. Acceleration is the second derivative. Okay. Find all intervals when the speed of the particle is increasing. So this is what we got to find. Speed of the particle is increasing. Okay, and remember, we have the graph. This is the derivative graph. Okay, so what does that mean? What does that mean speed is increasing? There you go. When speed is increasing, when velocity and acceleration have the same sign. Right there, here, or here. Same thing. All right, same sign. They're both positive at the same time. They're both negative at the same time. Okay, that's what we got to figure out. So let's go back to the graph. So let's figure out signs. Let's figure out signs for velocity. When is velocity positive? When is it negative? I don't want to use green. Let me use blue. So blue is when it's positive. Orange is when it's negative. Okay? So when is velocity positive? How do we know when this guy is positive? When it's above the x-axis. Yep. This is the velocity. So when velocity is positive, that's just above the x-axis. Okay? So here, it's 0. Looks like it's 0 at 9.5. But then it picks back up. And the opposite would be negative. Okay? So blue is when velocity is positive. Orange is when velocity is negative. Okay? Now, next thing is, when is acceleration positive and negative? How do we know when acceleration? So acceleration is this guy's derivative. So when is acceleration going to be positive? When it's going uphill, increasing, yep. Decreasing means negative, okay? So it looks like it's increasing up until here, then decreasing around 9, then increasing again until about 12. Okay, so in this first little quadrant, acceleration is positive, then acceleration is negative, acceleration is positive, acceleration is negative. Those are the changes. Okay. So now our job is to figure out where they have the same sign. All right, so let's look in this first little quadrant area. From 0 to 4. From 0 to 4. So blue means positive. Blue means positive, orange means negative. Well, from 0 to 4, acceleration is positive because it's going uphill. What color is also positive? Blue, right? Blue. So blue goes from 1 to 4. Okay, so we got 1 to 4. Write that down. Okay, now the second one. The second between these two guys here. Okay, acceleration is negative. Is there any velocity negative there? No. So they don't share signs there. So nothing there. So this guy is not going to give us anything. Okay, let's go to the next one, the smaller segment. Velocity is once again positive, and acceleration is also positive. So from 9 to 12, they have the same sign. And then the last piece from 12 to 18. From 12 to 18, acceleration is negative. And negative is orange. So this is negative, and this part right here down here is negative. So from 17 to 18. Okay, so we say particle speed is increasing from because velocity and acceleration have the same signs, or the same sign. They're both positive or they're both negative. Okay. Okay, so try number 7. We haven't done negative acceleration, but you can do it using the negative acceleration. So they want to know, when is acceleration less than 0? Okay, so I want you to try this one on your own, see what you get. These are the inflection points. Okay, try that on your own. I'll give you a few minutes and then we'll go over it. Again, just try the best you can. If you're not using the front page, that means you've memorized all the front page, and I don't think you have. So use the front page. That's what it's there for. Okay, so what is the relationship between position and acceleration? Second derivative, right? So what does that mean in terms of a graph? What does that mean in terms of, what does second derivative mean in terms of a graph? What does first derivative mean in terms of a graph? But what does that mean though? So if I say this graph is a derivative of another graph, what is it? Slopes, right? Slopes. This guy was the slopes, right, of position. Slopes increase and decrease, right? First derivative test, increasing, decreasing. Okay. Well, this one is not that. This one is the second derivative. So what does this tell us? So what is the relationship between this graph and second derivative? Okay, so if the first derivative is slopes, positive slope increasing, negative slope decreasing, where have we heard that? Increasing, decreasing. First derivative test, right? First derivative test. Okay. What is the second derivative though? Concavity, concave up and concave down, right? Concave up and concave down. So the relationship between position and acceleration is concavity, concave up or concave down. The second derivative test, right? The second derivative test. So the second derivative test checks for concavity. When is something concave up? When is something concave up? Let's write this down. Concave up. When is something concave up? Okay, so but what has an increasing slope? You're right. When something's positive, what is positive? Not the y value. The second derivative, right? When the second derivative is positive, that goes back to our justifications, right? Isn't that a justification for concave up? When the second derivative is positive? When the second derivative is negative, it's concave down. That's what the second derivative test is all about. So what we have to do is figure out where in the world is this concave up and where is it concave down? Well, what signifies a change in concavity? What signifies, okay, I change from one to the other? So close. What signifies, that signifies a change in the first derivative test, right? Those are critical values. Same thing, but for second derivative tests. What signifies a change from concave up to concave down or concave down to concave up? No. Point of inflection, right? Point of inflection. Do we know where the points of inflection are? We do. They told us, right? They told us on the last problem. We didn't use them, but we're going to use them now. So those green dots signify a change in concavity. Okay? So let's go before the green dot. First green dot. From this green dot to this green dot. Or sorry, from the beginning to this green dot. Is that concave up or concave down? Is it holding water or spilling water? Concave up, right? Okay. So let's write this down. It's concave up. So that means the second derivative is positive. Second derivative is positive because it's concave up. It's holding water. Okay. Let's go to the next, from green dot to green dot. This part here. Holding water or spilling water? That one's the next one is spilling water. Spilling water, that's concave down. Okay, let's go to the next one. From the next green dot to the next green dot, holding water or spilling water? That looks like it's holding water. This one looks like it's holding water. It's a cup. Is the cup up or is the cup down, right? It's kind of a cup up. So this is going to be, oops, why did I put acceleration? Next part. That one's spilling water. And then the last one, from the last green dot to the end, holding water. we have 1, 2, 3, 4, 5 different sections. So we change 1, 2, 3, 4 times. There's 4 changes where we change in concavity. So we want where it's negative. Negative means concave down, concave down. So that's going to be 2 spots, right? That's going to be in the pink. So you say negative acceleration from 5 to 7 or 9 to 11. Because second derivative of the graph is negative. That's the justification. Every time they ask you about acceleration, your justification is always going to be about the second derivative. Okay? Every time they ask you about velocity, your justification will always be about the first derivative. Okay? So on this, let's see, let me go back real quick. I'll come back, but let me go to where we wrote all of our justifications and stuff. So the ones that say critical points, relative maximum minimums, relative maximum minimums, increasing, decreasing, these could also work for velocity. These could also work for velocity because velocity is the first derivative. And then the rest of them not that one, could work for acceleration because those guys are acceleration, right? These are all related. They're just using different terms. Instead of second derivative, they're saying acceleration. Instead of first derivative, they're saying velocity. Okay, so anytime you see the word velocity, it's the first derivative. Anytime you see the word acceleration, second derivative. Position, original, f of x. Okay, so even though it kind of seems different than what we did here, it's the same thing. The justifications are all the same. If they ask me to find where is velocity positive, that's increasing. Where is velocity negative? That's decreasing. Where is acceleration negative? That's concave down. Where is acceleration positive? That's concave up. So they're all related. This lesson and that lesson are like the same lesson. They're just using different terminology. That's it. Okay? So it's the same lesson, different terminology. Okay? All right, let's do example number 8. Let's look at another graph. One of the most important things to do is read what you have. Read what you have, then read what we need. What do we have? What do we need? What do we have first? What do we need next? Because sometimes you don't have to do that much work if you've forgiven a lot. Sometimes you got to. Okay? So this is the position graph. This is the original graph, a graph of the original. Okay. The green dots are the dots there are inflection points. When is the particle moving to the right? So that's what they want us to do. They want us to find when the particle is moving to the right. I have no idea what that means. Where could I find that out, what it means though? First page. So what does it mean when it says the particle is moving to the right? Velocity is greater than 0. Positive, right? That's what we need to find. When is velocity positive? When is velocity positive? This is not velocity. Velocity is the first derivative of this graph. So how do we find velocity on this graph? Positive or negative. I don't care what. I don't care if it's positive or negative. If I know where it's positive, I also know where it's negative. So how do I use this graph to find out where velocity is positive or negative? There you go. Increasing, decreasing. Good. Increasing, decreasing. Where is it increasing? Where is it decreasing? First derivative, right? Because this guy is the original. Velocity is the first derivative. First derivative test. That's what you guys just did. Good. Okay. So where is it increasing? Where is it decreasing? Okay. So if you have a highlighter, it's nice because you just highlight. If you don't have a highlighter, just break it up into little parts like I did earlier. Looks like it's increasing from 0 to 4. And then decreasing from till about 7. And then increasing up to 10. And then it looks like it continues to decrease. At 13, it kind of stops. So at 13, it's not really increasing or decreasing. So velocity is positive here. Velocity is negative here. Velocity is positive here. And velocity is negative here. Right? First derivative test. What we just did was the first derivative test. That was the first derivative test. But it was just on a graph. So it looks different. Okay? When I do the first derivative test, that's all I'm doing. Where is the original increasing and decreasing? Right? Second derivative test is where is it concave up, where is it concave down, which you guys just did here. That's the second derivative test. Okay. So where is velocity positive? Let's see. Particle moving to the right from 0 to 4, 7 to 10, and that's it. Okay. Mm-hmm. No, because is it increasing or decreasing at 13? Yeah, it's still 0. It's 0, so technically 13 isn't even positive or negative, it's 0. But it's for this question, it doesn't make a difference yet. For this question, it doesn't make a difference because they didn't ask us about negative. So just where it's going uphill. So our justifications are exactly what we said. Because first derivative is positive. Well, instead of f prime, what are we going to write? Velocity, yep. V of t. Done. Okay. So sometimes, like I said, today they gave you original graphs. We're used to seeing just derivative graphs, right? Sometimes they'll give you the original graphs. When they give you the original graphs, do the first derivative test and the second derivative test, just like we did on here. Okay, and if you're not sure, you don't remember, that's why I'm recording this. Just go back and watch the video, right? Just watch the video for a little bit, kind of get your brain going. You're like, oh yeah, okay. Then you can go back to it. Okay. Okay, so last one. Last one we'll do today. We'll finish this today. Okay, last question. All right. So this is a physics question. It's a physics, things falling, right? I stole this from Mr. Yates because he's a nerd. To save his son Luke Skywalker from certain death, Darth Vader picks up the Emperor and throws him off a ledge onto the Death Star. Okay? As he falls, the Emperor's position S is given by the function S of t, where S is measured in feet and t is measured in seconds. Okay? Okay, so original, we're given the original, right? Position. So if I want to know where he's at, location-wise, that's what I'm going to use. If I want to know how fast he's going, I need velocity. If I want to know how fast is his rate changing, that's acceleration. Okay? So the first question says, what is the Emperor's displacement? That's a word we haven't seen before. From 1 second to 2 seconds. Displacement is something we haven't talked about yet, but it's on that first page. It's on that first page. So if you go back and look at the first page, I believe it's towards the bottom. Middle. There we go. Yep. Yeah, right under speed. Displacement is how far you are from where you started. So if I'm here, and then 2 seconds later I'm here, my displacement would be how far would I just come? Distance, that's it. Just distance, not a rate. Okay? That's what we need to find out. So from where is he from one time to one time? Oops. So how are we going to figure that out? I want to know, where are they now? Where were they then? What's the difference? What am I going to use? Yeah, I have 3 options. I can use position, I can use velocity, or I can use acceleration. Which one of those 3 tell me about where I'm at? Position, right? Position does, right? So I'm going to use position. How do I know where he's at 1? Plug it in. Plug it into position, yeah. Plug it in 1, plug in 2, subtract. So essentially, this is what we're doing. We're doing S of 2 minus S of 1. That's essentially what we're doing. We're plugging in 2 for S, or for T, sorry, and plugging in 1 for T, subtracting them. So negative 16 plus 16 plus 320 equals positive 320. Plug in 2. Okay, so negative 16 times 4 now, plus 32 plus 320. So negative 16 times 4 is negative 64, plus 32 plus 320. That would be negative 32, negative 2 something, or positive 200, see, 320 minus 32. $288. Okay. So if I start here and end here, and I want to subtract them, you start with the one where you're at, right? You start, where am I at here, minus there, right? So that's how you do it. So you go, where are you at? So 288 minus 320. And that's negative 32. Since it's only distance, feet. Does it make sense that it would be a negative number? Negative distance. What is he doing? Where is he moving? Where is his body moving? How is his body moving? He's falling down, right? says he's fallen off a ledge. He throws him off the ledge. So at 1 second, he's up here somewhere. At 2 seconds, he's down there somewhere. So does it make sense that he's going in the negative direction? Yeah, so that makes sense, okay? Always check to see if it makes sense. Okay. When will the emperor hit the ground? So when will the emperor hit the ground? Okay. So this one doesn't say, so they want to know when he's going to hit the ground, right? Okay, so let me draw a little picture here. Pictures help a lot, especially when you're trying to figure out when and where. Okay, so I'm going to draw a little graph, but essentially it's just what's going on here. Oops. Okay. Okay. Falling off the ledge, right? Falling off the ledge. So at time 0, he's on top of the ledge. Our equation is a quadratic. Quadratics are parabolas. They're U's. Either they're this arrows up U's or arrows down U's. A happy face or sad face. This one's not going to be a U. It's going to be half a U because he starts at the top, right? So it's going to be kind of like that. All right. So this is time 0. And this is what I'm trying to find. When will he hit the ground? This is time. It's half a parabola. It's half of a parabola. I know this was a while ago, but go back to your Math 2 or Math 3 days. What is that red dot going to represent? Don't even think in terms of velocity. I'm not even talking about velocity, or just think of what does that dot represent? The x-intercepts. Good. How do we find the x-intercepts? Set it equal to 0. That's what we're going to do. Solving. That's essentially what we're doing. Yeah, solving. So S of t is negative 16 t squared plus 16t plus 320. We're going to set it equal to 0. I'm going to solve it like I would a quadratic. Trinomial. I think all of them can be divided by 16. Let's see. Yeah, so they all can be divided by 16. So GCF is negative 16. So that makes positive t minus 1t minus 20 equals 0. So let's see. I'm looking for the two numbers that multiply to be negative 20 and add to be negative 1. And yep, negative 5 and positive 4. So t minus 5 and t plus 4. I'm going to get two answers. What are those two answers going to be? Positive 5, negative 4. Which one is the red dot going to be?
5.
Why 5?
It's not negative. It's not 0.
There you go. It's positive. Has to be 5. That guy has to be 5. Because negative 4 can't go back in time. We can't go back in time. So the only one that's valid in our purpose is 5. So when will he hit the ground? At time 5. What is it? Didn't they give us, what is time in this case? They said time, right? Seconds, right? So we always want to label. Emperor will hit the ground at 5 seconds. So if they give you units, always use units. They didn't give us units earlier, so we didn't worry about it. But yeah. Okay, that's just the equation I'm using. That's just the gravity equation. That's just the equation for gravity. So if you want to know anything, any time about anything, that's the equation you use, right? So if you're falling, if you throw a ball into the air and it comes back down, that's gravity. Gravity brings it down, right? That's the equation for gravity. So that's where they got the equation. It's just the gravity equation. Okay. Okay. So now, what is the Emperor's velocity at impact? So a couple buzzwords there: velocity, impact. What do we know about velocity? First derivative, right? So that means it's going to be s prime of t. Good. What do we know about impact? Okay. What else do we know? At 5 seconds, right? T equals 5. So what do you think we're going to do? There you go. Find s prime of t, plug in 5. So what is it? Negative 32t plus 16. Was that 160? Negative 160 plus 16. Negative 144. What are the units going to be for this guy? It's a rate. Velocity is a rate. So when you drive your car, what units are you using? Miles per hour. He's not driving a car. What is he going to use? Yeah, put the distance first, time second. So distance over time. So feet per second. Yep, feet per second. Does it make sense that it's a negative number? What is his direction? Positive or negative? Down. Yeah, negative. So it makes sense, right? What would the speed be? What is his speed at impact? Positive 144. Positive 144. That's how speed and velocity are related. It's just if it's negative, make it positive. So 144 feet per second. That's pretty fast, right? Every second, he's covering 144 feet. 144 feet is probably from here to the fence over there. In 1 second, he's covering that distance. That's fast. Okay, that's pretty fast. Okay. Next question, what is the speed at impact? Yeah. Yep. Same thing though. Speed always has the same, right? What is it? Feet per second? Right? Because speed equals the absolute value of velocity. Last question. I hope. Yes, last question. We'll be done. Acceleration as a function of time. So what they mean there is give me, they don't give me a specific time, right? So if they don't give you a specific time, they just want the equation. Give me the equation for acceleration. Okay? So what do we know about acceleration? Second derivative, right? Second derivative, s double prime. So S prime was negative 32t plus 16, right? So that means this one would just be negative 32, right? Does anyone know what the units would be for acceleration? It's a rate. It's kind of a funky one because it's a rate of a rate. It's not just a rate. It's a rate of a rate. So we always start with distance. So what's the measure of distance they're using? Feet. And then we do time. What's the measurement of time they're using? Squared. Time squared. It's distance over time squared. So acceleration is always distance over time squared. Velocity is just distance over time. Position is just distance. And you're done. So that was just a little, it was kind of the same, but a little different because of the, you have to figure out when he hits, but that's just you're just solving a quadratic. So it wasn't too bad. Okay. All right. So tomorrow, all I'm going to do is just give you time to work on this assignment. Okay. I'll post the answer key tomorrow so you can look at it. You can work on it if you want to, but like I said, I'm not going to officially assign it until tomorrow. I just wanted to give it to you